We have now come to logarithm. Logarithm is an integral part of mathematics to any level. It is very important to understand logarithm. It is useful in every branch of science, even the biological side. It's even useful in economics and other branches. Logarithm is highly connected to indices. Now, when we are working, most times, we talk about change of subject of formula. Look at this. If I have A, B equal to C, and I want to make A the subject of formula, I divide both sides by B. So I have AB over B is equal to C over B. Therefore, A equal to C over B. That is it. Now let's talk about power. If I have x equals to y raised to power a, and I want to make y the subject of formula, it's easy. I just divide the powers of both sides by a. So what am I saying? So I have x raised to power okay, x raised to power 1 equals to y raised to power a. Therefore, x raised to power 1 over a is equal to y raised to power a, which is y raised to power 1. Therefore, x raised to power 1 over a is equal to y, or a is equal to y. That is x root a. In the root a of x is equal to y. But if you want to make a the subject of formula, how do we go about that? That is where the word logarithm comes in. That's where the word logarithm comes in. Now, if I have, so what am I saying? If you have y x equals to y raised to power a, and I want to make a the subject of formula, let me now work this. Log yx equals to log y raised to power a. Just follow the place, which is a log y. And what does that give you? It makes this one is equal to 1. You get to that. A will be equal to log y of x. Log x to the base of y. So with this expression now, we have been able to also make a the subject of formula. We have this in calculators and our tables. And by the time I work so many other ones out, you will understand this more. So we have this expression now. That is, if we have y equals to x raised to power a will be equal to log to the base of x, y. I am trying to make you to see this thing very well. Then, let us now look at what are the conditions, what are the kind of rules that exist in logarithms. 1. If I have x equals to x raised to power 1, then I want to make 1 the subject of the formula. So I have 1 will be equal to log x. So when you see any logarithm with the same base, the answer is 1. So let's make this one our first rule. That is, log of any number to the base of the number is equal to 1. Let's look at another thing that can exist. We have 1 equals to x raised to power 0. X raised to power 0. Then, we can now say log x1 is equal to log x raised to power 0. I want you to also look at something now. This 0 will come here because this one is the base. So 0 will be equal to this one will be equal to 0 times log of x. Therefore, log of any number, log of 1 to the base of any number is equal to 0. Let's make that one our second rule. So when you see anything like this, when you want to make any number, to find the log of 1 for any number is 0. Log of 1 for any number is 0. Now let's continue. From this one, the first one now, let's look at another thing that can happen. Let us say we have a number like z is equal to x raised to power b. Z equals to x raised to power b. So let us now find log to the base of x for both. So log x z will be equal to log x raised to power b. I want you to look at something. With this power, since the power is what you have been working on, log x z from our real expression is going to be b log x. Are you getting that now? Just from our major definition. Therefore, log x z is equal to b. I want to reiterate this now, but I want to connect it to this. this place. Are you getting it now? Therefore, if z is equal to x raised to power b, log xz is equal to b. And not just b, let's say log x. What I'm trying to reiterate is this power is used to multiply this. And you know this one is equal to 1. That's why I was stressing it the other time. Once you get this, you can solve so many things in logarithm. Let's now talk about addition, subtraction. Yes, of logarithm. 4. Let us pick two numbers, m and n, and they are of the same. They are, powers of x. Let's say m equals to x raised to power a, n equals to x raised to power b. You understand? And let us talk about mn. Mn will equal to x raised to power a plus b. Therefore, log mn, its products, is equal to a plus b. And log xmn, log xm is equal to a. Log xb, log xn is equal to b. So, log xm plus log xn is equal to log x products n times n. So what are we trying to say? We are saying that log of products is equal to sum of log of individual figure. That is what that is saying. So log mn is equal to log xn plus log xn. So log is mainly for products, division, powers. You don't use log for addition. You don't use log for subtraction, because addition of log is for products. Subtraction of log will also be equally for subtraction and for division. Now let's look at the what I call the fifth one. We have this log xn is equal to a, log xn is equal to b. So n over n is equal to x raised to power a minus b. So log n over n x is equal to a minus b. Therefore, log xn minus log xn is equal to log xn over n. So you can see that it's just tied to indices. That's why we always try to work the two of them together. Now let's look at another one. If n equals to x raised to power a, then n raised to power k will be equal to x raised to power a k. But from this place, we realize that log x n is equal to a. So log x n raised to power k will be equal to a k. Or you can just say, because this is power, log x n raised to power k is equal to k log x n. And you know that log x n is equal to k a, so which is equal to k a. Please, I'd like you to note the connection here. This one is the most important one. Every other thing I derive from that perspective. So we have this one also. Let's say that a is raised to power log ax. What will it give us? Now, let us take this one to be equal to b. So a raised to power log ax is equal to, okay, let's say f. What will this f be in terms of a or x? So let's make the both sides to be in terms log of ax of a. So we have log a raised to power x is equal to log a f. Then it will be log a x log a. Sorry, log a is equal to log a x. Please, log a raised by log ax, I equated that one to be f. So I now work both sides to log a to the base of a, log of base of a. So this one is log a to raise to the power of log ax is equal to log af. So log ax, that is this power now, I brought it down, multiplied to log aa is equal to log af. And log aa is equal to 1. So I have log ax is equal to log af, which implies that x is equal to f. What does that say? What it means is that when we raise anything to the power of its base, that is log a raised to the power log ax is equal to x. So if you are given anything like this is the answer straight. Don't stress yourself. Let's look at something now. Let's say 2 raised to the power log 2/8. You have it. What it means is that after working it through like this, you are going to have 8. Let's work it out and see how it pans out. 2 raised to the power log 2/8 will be equal to, let's say, c. So log 2/8, so log 2/2 is equal to log 2c. And this one here is 1. So I have log 2/8 is equal to log 2c. So invariably, when you compare the two equations, c is equal to 8. So that is another rule, and it's very straightforward. Just know this thing, know the proofs. I don't subscribe to cramming rules, but just know the rules. In case you have any itch, you'll be able to find your way out. Now let's look at another one. We have y equal to x raised to the power c. Therefore, log x y is equal to c. From this one again, I can say x equals to y raised to the power 1 over c. Therefore, log x to the base of y is equal to 1 over c. If you look at this, it means that this one is reciprocal of this. Therefore, log y to the base of x is equal to reciprocal of log x to the base of y. So you can see the connection now. I think this might be the 8. This might be the 8. The 8th rule. For change of base, let's look at the first one. If a is equal to b raised to the power c, then c is equal to log a to the base of b. X equals to a raised to the power d. Then d will be equal to log a raised to the power log x to the base of a. But if you look at the two, this is a. X equals to a raised to the power d, which should mean that b raised to the power c, b, c, d. But log ax log bx will be equal to cd. Please look at this. Log bx will be equal to cd, or let me write again. X equals to b raised to the power cd. Therefore, log x to the base of b will be equal to cd. And if you look at this case, we have expression for c and d already. So log bx will be equal to log ba times log ax. So it's just like share rule, ba ax. So if you are changing the base, of logarithm, assuming this was in log ax, and you want to change it to log bx, this is just how you go about it. That's just how you go about it. Let's look at the other format. So as I was saying, if you have log ax and you want to change it to log bx, so it's going to give you, this is how you do it. It will just be log b of this a times log ax. So that will give you log bx. And in some instances, you are not even from your tables, you might be compelled to work out like this. If you have just table that has one form of logarithm and does not have the other one, you want to find logarithm to the base of another figure, you will use this formula. Now let's look at another format. I call that one change of base again. You know that ax is equal to log ab times log bx. Log ab times log bx. And we know one thing from the 8th rule that log ab is equal to 1 over log ba. So log ax is also equal to log bx over log ba. Log bx over log ba. So these are the commonest rules to work with in logarithm. And I advise that if you copy out each rule as a summary to look through and to prove. Now let's look at what we can work out using these rules. Now let's run through the summary. If y equals to x raised to power a equals to log xy. If n equals to x raised to power a and n equals to x raised to power b, log x product of m and n is equal to log xn plus log xn, that is a plus b. Also for the division, is going to be log xn minus log xn, a minus b. So this are also facts. Log x base x is equal to 1. Log 1 base x is equal to 0. A raised to power log ax is equal to x. If a equals to x raised to power n, a raised to power n is equal to x raised to power mn. Therefore, log xan will be mn. mn. Now, log y base x is equal to 1 over log x base y. Log x base b is equal to log a base b times log x base a. And it's also equal to log x base a over log b base a. So that is all. This one is even easy. Just chain rule. When you know that chain, you get the answer. Now let's just use this as refreshment. We have this. The first one says that you should find log 264. Let's equate that one to the x. Therefore, 64 is equal to 2 raised to power x. You know the definition of logarithm. But 64 is equal to 2 raised to power 6. And that is 2 raised to power x. So equating the powers, x is equal to 6. Therefore, log 264 is equal to 6. Very straightforward. Now let's look at the second one. It says log 10x minus log x10 is equal to 3. And from our knowledge, you know what this implies. Log 10x minus 1 over log 10x is equal to 3. Remember, change of this, the inverse. Now, we can now multiply through by log 10x. So we have log 10x squared minus 1 is equal to 3 log 10x. So, because if this one had been just like ordinary number, it would have been easy. But you have log 10x times log 10x. That compels us to express it like this. So that is why I also make this one to be outside. I would have said log 10x cubed. So let's leave it like this. Let's make log 10x to be equal to y. Therefore, y squared minus 3y minus 1 is equal to 0. So I got y from this place. And if you come back here, you see that this is log 10. So x will be equal to 10 raised to the power 3.303 or 10 raised to the power minus 0.3028. So x will be equal to 2009 approximately or 0.49854, approximately 0.5. So x is approximately 2009 or 0.5. So that's the answer. Now let's treat these questions. 1, 2, 3, 4, and 5. I want to let you know something. When you see log and the base is not there, they are talking about base 10. They are talking about base 10. So if you see anything like this, log 5, what they are saying is log 5 to the base of 10. That's what it means. So take notes. We are still going to common logarithm. But before then, let's treat this one. If log 318 plus log 33 minus log 3x equals to 3, find x. The solution is this. We know that where they are in the same base, all these ones will be product and division. So we have log 318 plus log 33 minus log 3x equals to 3. Therefore, log 3 into 18 times 3 over x is equal to 3. So we have 18 times 3 over x is equal to 3 raised to the power 3, which is 27. And that is 27. So x will be equal to 18 times 3 over 27. So x is equal to 2. We have solved the first one now. Let's go to the next one immediately. So we are using the rules of logarithm to solve all these things. I'm just trying to show you the application of the rules. It says evaluate log 112 if log 2 equals 0.3010 and log 7 equals to 0.8451. They are giving us the logs of each number. So let's break 112 into its factors. 112 is equal to 2 times 56, and which is 2 times 8 times 7, which is 16 times 7, and that gives me 2 raised to the power 4 times 7 raised to the power 1. And so log 112 will be equal to 4 log 2 plus log 7, which is 4 into 0.3010 plus 0.8451. That gives me 1.204 plus 0.8451. 194140. So that's the answer. So log 112 is equal to 2.04991. Now let's solve this. We have this question: evaluate log root. Log 4 to the base of root 2, 16 base of half, and log 20 to the base of 4. So we have it like this: log root 2 plus log half 16 minus log 132. So that will give me log of root 2 to 2 raised to the power 2 plus log half to 2 raised to the power 4 minus log 4 to 16 times 2. So, and you can see that this one is going to be log root 2. Root 2 raised to the power 2 times 2 log half raised to the power minus 1, because 2 is half raised to the power minus 1 times 4 minus log 4 to the base of 16, you know, from our laws of or roots of logarithm. So this one is going to give us 4. This one is going to give us minus 4. This one is minus 2. Because, okay, let me continue. Log 4 is to the power 2 minus log 4 is to the power half. So this will now give us 4 minus 4 minus 2 minus half. So everything is minus 2 half. And that's the answer. So log 10 x minus 3 plus log 10 x minus 2 is equal to log 10 2x squared minus 8. So what is this telling us? It's just telling us that the product x minus 3 x minus 2 is equal to log 10 2x squared raised to the power 8. And since they are in the same base, you put this one and this one will be equal. So we have x squared minus 5x plus 6 is equal to 2x squared minus 8. So let me transfer this one here. So I have x squared plus 5x minus 14 equals 0. So after doing the factorization, x equals to 2 or minus 7. So we have this question: log 10 2x raised to 2x minus 2 bracket plus log 10x plus 4 equals to 2. Second, log 10x squared plus 1 bracket minus log 10x squared equals to 1. Express log AB in terms of logarithm to base 10. Given that log 10 2 equals to 0.3010. Calculate without using tables the values of to 2 decimal places of log 2 0.64 and log 5 root of 1.25. And the last one, solve log 2x plus log x 2 equals 2.5. Let's start from the first one. So we have log 10 2x minus 2 plus log 10 x plus 4 equals to 2. So just like the other one we did, the product of this. So we have log 10 2x minus 2 into x plus 4. You know, when we add log, it means product of these numbers is equal to 2, which is equal to 2 log 10 10. which is log 10 x squared. At the end of the day, the product of this is going to give us that last number. So we have 2x squared plus 8x minus 2x minus 8 is equal to 100. Please, the expansion of this, that's what I'm working out here. So 2x squared plus 8 minus 2x minus. So what do I have here? I have 2x squared plus 6x minus 8 minus 100 is equal to 0. So I have 2x squared plus 6x minus 108 equals 0. I can also say x squared plus 3x minus 54 equals 0. So if you look at it, we have x squared plus 9x minus 6x minus 54 equals 0. So I have x into x plus 9 minus 6 into x plus 9 equals 0. So x minus 6 into x plus 9 equals 0. Therefore, x equals to 6 or minus 9. X equals to 6 or minus 9. That's all the first one. Now, we have log 10 x squared plus 1 minus log 10 x squared is equal to 1. So let's solve this. So this gives us log 10 x squared plus 1 over x squared is equal to 1, which equals to log 10 10. So, which means that x squared plus 1 is equal to 10x squared. Therefore, 1 equals to 9x squared. So x squared is equal to 1 over 9. X squared is equal to 1 over 9. Therefore, x equals to root of 1 over 9, which equals to 1 over 3 or minus 1 over 3. And in this place, okay, or minus 1 over 3. Now, the third one says that you should express AB in terms of logarithms to base of 10. So log AB is equal to, so log AB is equal to log A10 times log 10A, which should be equal to log 10B, sorry, times log 10B, log 10A times log 10B, which is equal to log 10B times 1 over log 10A, which is equal to log 10 b over log 10A. That's how that one is handled. Now let's look at the other part. It says log 10 2 is equal to 0.301. It now says calculate without using tables the values of 2 to 2 decimal places of log 2 0.64 and log 5 with 1.25. So log 10 log 2 0.64 will be equal to log 2 64 over 100, which is equal to log 2 64 minus log 2 100. And if you look at this, what is log 2 64? That is log 2 2 raised to the power 6 minus, we have this log 100 over log 10 100 over log 10 2, which is equal to 6 minus 2 over 0.301, and that will give us, and that gives us 6 minus 2 over 0.301, and it gives 0.6445. That's the answer for the first one. Let's do the second one. So we have log 5 root of 1.25, but we are only given that of log 2. Let's see what it will be. Log 5 root 125 is equal to log 5 1.25 raised to the power half, which is half log 1.25. So if we express this one further, it's going to give us half log 125 over 100. Oh, log 5, sorry. Log 5 125 over 100, which is equal to, I'm trying to make it in the part of 5 that is possible to bring it out. It's going to be half log 5 there is 25, 5 there is 20. And it can still be simplified. It's half log 5. 5 there is 5, 5 there is 4. So it makes it very easy now. Therefore, I have half log 5 minus log 5 4. This half affects everything inside. So it's going to be half log 5 5 is 1. And I have minus 2 log 5 2. Very simple. So at the end of the day, I can bring this to be 0.5 and this one is 1. So I don't carry that one around again. 0.5 minus log 5 2. And this will now give me 0.5 minus log 10 2 over log 10 5. If you look at it, I can still bring 2 out. It's going to be 0.5 minus log 10 2 over, this is 1, this is 10 divided by 2. Log 10 10 minus log 10 2. This one alone. So that's how it stands. I can still simplify further. It's going to give me 0.5 minus, that one is 0.3010. Log 10 10 is 1 minus 0.3010. So on dividing this by this, I got 0.5 minus 0.4306, and that's my answer, my final answer. 0.0694. Now let's work this out. Log 2x plus log x this part n log 2 base x is equal to 2.5. So we can work this out and say log 2x plus 1 over log 2x equals to 2.5. Now multiply through by log 2x. So log 2x squared plus 1 is equal to 2.5 log 2x. So let's make our log 2x to be equal to y. So we have y squared plus 1 is equal to 2.5 y. So y squared minus 2.5 y plus 1 will be equal to 0. And from here, I can still make it simpler. Let's try. So 2y squared minus 5y plus 2 is equal to 0. So two figures that give us, that is not give us minus 5, and equal to give us. So let's try. So 2y squared minus 4y minus y plus 2 is equal to 0. So 2y into y minus 2 minus 1 into y minus 2 is equal to 0. So you have 2y minus 1 to y minus 2 is equal to 0. So y equals to half or 2. So you can see it's very easy and straightforward. So logarithm is very useful in so many branches, and that's why we treat it as a special topic. We go on to some other logarithms. Very simple. These are the main laws. The other one is just to make it simple and application. So we talk about natural logarithm and common logarithm. Now let's talk about natural logarithm. We always express it as ln, ln. Ln is logarithm of number to the base of n, that is log e x. So instead of writing it out like this, we write ln x. Ln, this natural number plays vital role in so many analyses in science generally, mathematics, physics, engineering, everything. So that's why we undo it separately. The number e is 2.7182818 like that. And e expansion of e raised to power x is this. When we get to series, we will undo all of this. So this is how we get natural logarithm. You can work with natural logarithm as any other logs, but because of its significance in analysis like calculus, it has made so many other things to be able to, it has made scientists to be able to achieve many things in analysis, like in electricity, charging and discharging, also in radioactivity. That is why we talk about ln. You can work with it. You can use ln when it comes to logarithm. If that's the only table you have, you can use it to work out so many things. That is why we talk about ln. Nothing much. It's the same thing like the other ones, but it's a special logarithm that we work with in mathematics. Place this. It's going to give us this. So that is what makes it so special. So if we have done integration or differentiation before, that is calculus generally, that is why natural logarithm is of special interest to us in STEM. Now let's talk about common logarithm. Now let's talk about common logarithm. Common logarithm is when we are talking about logarithm to the base of 10. Common logarithm is about logarithm to the base of 10. Logarithm to the base of 10. And since we know that logarithm is derived from logarithm, logarithm base 10 to be very interesting. You know, one of the numbers that we use universally everywhere is number 10. So it makes it very good, very useful, and let me say important to be able to work in log of base 10. Therefore, we will talk about one aspect of indices which is very, very important. We call it expression of numbers in standard form. In standard form. So, what does that mean? It means that if we have a number a, we should be able to express it as k times 10 raised to power n. This k, you can easily derive it from here. This n, you can easily derive it from here. You don't need any special schooling before you work it out. That is standard form. And k is always greater than 1. Okay, let me make it like this. K is greater than 1. K is greater than 1 and less than 10. So which means that k is between 1 to 9.9999. That is k. Let's look at some numbers. So n is integer. So it can be negative, it can be 0, it can be 1, it can be anything. Let's look at numbers like this. 313. If you have to express it in standard form, it's going to give us 3.13 times 10 raised to power 2. That is 3.13 times 100. And 100 is 10 raised to power 2. That is the first step in understanding common logarithm. Let's look at another number. 0.0514. You know I said it. This k should be between 1 and 9.999, but never up to 10. So we have 5.14 times, if you look at it, from here, 1, 2. 10 raised to power minus 2. Straight, direct. Or if you can, it depends on how you work it out, but this is how you get it. So the most important thing is, you must be able to express that number in standard form. And from standard form, you will now be able to go and work in common logarithm. Any number. This is the first step. And then, if you now want to work in common logarithm, the numbers are divided into 3. We have mantissa, we have character. So we have character and mantissa. And with this, you are going to do everything in what they call logarithm. With this, you can do your multiplication, division, power, everything. Let's look at some things. Now, since I have 313, like I started with, I said it's going to be 3.13 times 10 raised to power 2. That is the first stage. The next stage now is this. From our tables, we can get this number to the base of 10. The logarithm of this number to the base of 10. So what does that mean? It means that we can get this one. It will be equal to a raised to power 10 raised to power a times 10 raised to power 2. This one here is 10 raised to power a, and we have 10 raised to power 2, which we got from just our observation from the number. But this other part, we get it from the table. So we call this one the character. And we call this one the mantissa. So we get this one from our 4-figure table. Let me tell you what. Let's look at a number like 2,000. 2,000 or 3,000. If I want to express this one in standard form, it's going to be 2 times 10 raised to power 3. That is it. And if I want to express everything in the powers of 10, this one is going to be 10 raised to power 0.3010. I got this from the table. Times 10 raised to power 3. Times 10 raised to power 3. So if I am expressing this one fully in log of 10, I can do that conveniently. So 2000 will be equal to 10. You know, when you have multiplication of numbers, you can sum the powers. 3.0, yes, 3.3010. So this is the character. This is the mantissa. So you have to really be able to know this thing. So when you are working with logarithm, common logarithm, you will just be working with ease. So if I'm now saying log 10 2000 is going to be 3.3010. Simple. Let's look at another one. If I want to get log 3000, it's going to be log 10 3 plus log 10 1000. This will give me my character. That is where the whole thing is. And this one, I get it from the table. So it's going to be 0.4717. I just get it from offhand. Plus 3. So at the end of the day, it's going to be 3.4717. So all I just want you to know is that this part, you get from table. It is always less than 1. Since you can get every other thing is up to 1, just from observation of the number. This part you get from the table. And this part you get from your standard form knowledge. After this, there will be a point you will need to convert it back to our common number in base 10. To our common number in base 10. Let's see how we do that. You know, I said it. The character can be any real, any integer. Can be positive, can be negative. So, we can now do this one, convert it to get the antilog of this, which means that this one will be equal to 10 raised to the power 2 times 10 raised to the power 0.3010. So we are going to get this one from our table, antilogarithm table. We have this one as 10 raised to the power 3 times 10 raised to the power 0.4717. So we can easily get this one from our tables. So for this one now, 2.3010 antilog will be equal to 100 times, if you check the table, this one is 2, which is 200. So you get this one from your table. Let's look at the other one. Antilog 3.4717 will be equal to, this one is 1000 times, and this one is 3. So it's equal to 3000. So let's see if we have numbers less than 10. It means this one will be numbers between 0 and 1. It means this one will be negative. Let's look at another number. Antilog. In this place, we don't always write it as negative, -2 or whatever. They have different meanings. When you attach minus, I will show you now. We write it like this, bar 2. So which means that one stands alone. 0.3010. So it is going to be 10 raised to the power -2 times 10 raised to the power 0.3010. You can see. So this one is going to be 2 times 10 raised to the power -2. And that gives us 0.02. No, I explained something now that we don't put it as -2 here. -2. Because if you put -2 here, you are giving it a different meaning. As this one is positive, and this one here is negative. Look at it. That is when we are dealing with negative power, negative character, or numbers between 1 and 0. Please note that. If you are written antilog -2.3010, antilog of -2.3010 is to give you this. But if it is from our workings, we get to this. The real answer ought to be this one is antilog -2 plus 0.3010. You can see that this one is different from this one. This one is different from this one. So we always work with this one. So this one is going to be like approximately antilog of -1.7. Antilog -1.7. So you can see -2.3010 is different from 1.7. Why? Because this side, the mantissa side, is positive, and the character side is negative. That is the one we use in our format here. If you use this, it will make our calculation much more, a little bit difficult, not too difficult. But with this, when you use your calculator, yes, you can use this one for convenience. But when we are using tables, this one is far better. Exactly. We shall see some examples. Now let's look at this. 0.02 times 3. If you are using logarithm, I'm just making it simple. It's going to be log 0.02 plus log 3. That's what that one will give us. Mainly for ease, we make it in tabular form. We say number log. So 0.02. What is our character? That is -2, bar 2. So we don't write -2, we write bar 2. Because this part is going to give us positive number. So this one will give us 2. And that is 0. That is plus 0.3010. Log 3. The character is 0. because 3 times 10 raised to the power 0. 0.4717. Look at what it will give us. It's going to be 7277 bar 2. Can you see? Bar 2. That is what it will give us. So at the end of the day, we are going to have, if we check from the antilog table, we are going to have, the answer will be 6 times 10 raised to the power minus 2. So you see, this one makes our power here to be easily derived, conveniently. That is what expressing it like this makes it to do. This is the only way you can work using the table. If you use minus straight, it will make your work a bit strenuous. But you cannot use this format to get your answer from the calculator straight, unless you have the knowledge of doing this, and then you find this one separately. You work with this separately. If you are using calculator, you find this one separately, and you can try it. Use calculator to find the log of this, and then you will see what it will give you. It's going to give you minus 1.2 something something, which is different from this. It's not that any of them is wrong, no, but the patterns are just different. Now, the area of particular interest in common logarithm is finding power, that is number raised to certain figure, like x raised to power n. You want to find y. What do we do? For you to find the value of y, if you know the value of log x, you just multiply n by log x. It will give you log y. This figure now, you will now find antilog of n times log x. You get this one also from the table, the antilog, and it will give you y. Let's just work one now. Let's say we want to find the value of 3.723 raised to the power 5. What do? We check number log. So 3.723, the character is 0. You get this one from the table. You might be given. Most times when you do this is when we are using tables. If not, your calculator will give you straight answer. So you go and check the tables. You check 3723. 37 under 2, difference 3. That is 5708. 5708. 5708. So because we are raising it to power of 5, you multiply this by 5. From this, you multiply it by 5. So, oh, sorry. This is what you multiply by 5. You multiply this one by 5, not this one, please. You multiply this one by 5. And then that's what will give us 4, 5, 2, 8. So this is the log of 3.723 raised to the power 5. Now, for us to now find this one now, 3.723 raised to the power 5, we have to check the fourth table for antilog of 0.8540. So you check 85 under 4, difference 0, times 10 raised to the power 2. And on checking, you can also do that from your log table, depending on the available resources. 8540. So that is 7145. 7145. 7.145. So the value of 3.723 raised to the power 5 is 714.5. 714.5. We can also use it to find roots. This one means 3.723 raised to the power 1 over 4. So you know what that is? That means now, if I want to find the fourth root of 3.723, I just divide the log of this by 4. So let's see. 3.723. So 0.5 708. So I divide this one by 4. So this is going to give me 0.14245. So this is 3.723. So that is for that one. I now check the antilog of this. So this is approximately 0.1425. So I will check for the antilog of this, and that is 1425. 1389. So 1.389 times 10 raised to the power 0. approximately 1.389. That's the answer. So, logarithm makes so many calculations easy for us in mathematics. Now, let's look at another number. If you have a number like this, 0.081, and you want to find, like, okay, fourth root of this. If you look at this, we write number log. That is going to give us 0.081. This is bar 1, bar 2. So we have bar 2 points. Let me get that of log of 81. And that is 9085. 9085. I want to find the fourth root of this. You know, if I start dividing directly by 4, if I divide by 4 now, it's going to give me 0.5 bar. Can you see? Plus 0.1, okay, 0.2, 2, again, 7, 1, you know, something like that. And at the end of the day, I'm going to have bar. So it has made everything clumsy. So the mathematicians sat down and they said, okay, fine. We have a way, we know the rules of logarithm. This is an easy algebra. Let's look at a better way of handling this. I'll show you now. When we have it like this, what do? We express it like this. Bar 2, you know, plus 0.9085. You can see this one is negative, this one is positive. To make it reasonable now, for us to be able to divide by 4, we add 2 to this one, subtract 2 to this one. You know that at the end of the day, it means the same thing. I'll show you now. Bar 2, no, plus bar 2, plus 2, plus 0.9085. You can see. So this one will now become our other parts for us to divide by 4. And this one will give us conveniently bar 1. So it's going to give us bar 4 plus 2.9085. Straight answer. Now let's divide by 4. What does that give us? Bar 1 plus, this one is 0.7. 2. 28. 7. Again, what? Let's say approximately 4. So we have approximately bar 1.7274. You can see. So when we find antilog of this, it will now give us the fourth root of 0.081. Let me get that. So 7274. That is 5338. So antilog of this is 5338 times 10 to the power minus 1. So 0.5338 square root, fourth root of 0.081. That's the answer. So when you come across anything like this, but had it been you were to divide by 2, you can do it straight. If you are to divide by 3, you will do the same thing. You will subtract 1 from this and add 1 to the side. That's the simple way of handling it. Nothing much in common logarithm again. The rules of logarithm applies. This is just the little manipulation we're using. I will do 1 or 2 examples to really show more. Now I want us to undo this. Cube root of 1.587 divided by fourth root of 0.008. Let's see what will happen. We'll undo it stage by stage. 1.587. You find logarithm of this. So 15 under 8 difference 7. That is 20. Okay. Yes, 2007. So since you are finding the cube roots, we divide this one by 3. And that will give us 0.0669. So this will be the log of 1.587 cube roots. So I can, for neatness, I can write it here, 0.0669. Now for this one, the log of 0.008, that's going to be bar 3 points, the log of 8, 9031, 9031. So since I want to find fourth root of this one, I will subtract 1 from this, add 1 to this. So it's going to be bar 4 plus 1.9031 over 4. So what the answer will be is 1 point, this one is going to be 4 because this one is 0.4. 0.4 in 30, that is 7. In 33, that is 8. In 11, approximately 3. So this is now the fourth root of 0.008. That is. Now, since they are dividing, you subtract this, the log of this, from this. So what does that give us? That gives us 6, 8, 8, 1 here. So this will be 9, 5. This is bar 1 now. Minus this, we have bar 2. I hope you understand. I subtracted this, gave me 6. I took 1 from here, gave me 8. 1 from here. And before I could take 1 here, I have to bring 1 here. So it remains 9. So this one is left with bar 1. So because I'm taking 1 from this, so bar 1 minus 1, bar 2. That is what it gave me. So let me now get the answer for it. So that is antilog of, that is 5886. 58 under 8 difference 6. That is 3464. 3.464 times 10 raised to power minus 2. That's the answer. That's the answer for this question. Cube root of 1.587 over. So this one is not connected to this thing, please. For 0.008. That's the answer. So let's work this out. So the log of 15 under 8 difference 7 is 2007. 2007. So to find the cube root of this, I have to divide this one by 3. And that will give me 0 points here. 0 in 26, 6, 9. That's what the cube root. Now, to find the fourth root of 0.08, I will find the log of 0.008, and that is by 3.9031. 9031. So, since I'm finding the fourth root, I will subtract 1 from this, add 1 to this, and that's going to be equal to bar 4 point plus 1.9031 over 4. And this will give me bar 1.9. That is 0.4. In 30, I have 7. In 23, I have 5. In 31, I have approximately 8. So this is now the fourth root of 0.008. Since I'm dividing, I have to subtract this one from this one. The log of this one from the log of this one. So what will that give me? This gives me 1, 1, 9. I have 9 here because I've taken 1 from this place. So I have 5. So bar 1 here, and this one is 0. So I have 0.5911. That is the log of this operation. Of cube root 1.587 over fourth root of 0.008 is 0.5911. So the actual answer is the antilog of this figure. So I get that one from the 4-figure table. 5911. And that is 3899 plus 1. That is 3.9. That is approximately 3.9 times 10 to the power 0, which is equal to 3.9. So our answer is 3.9. So what will make it easy for you is when you lay your table neatly, you'll be able to go through all the procedures with ease. Now let's work this out. So we start by getting the logarithm of 2.068. And what does that give us? 0.2068. That is 3156. 3156. So the square root, you have to divide this one by 2. And what will that give us? It's going to be 0.15 0.15778. That is the logarithm of 2.068. So that's the logarithm. Now, let us now work out for this other one. That is 0.58. That is bar 1. points. Let's check logarithm of 58. And that is 7643. 7643. Because we are raising it to the power of 4, we now multiply by 4. So that will give us, and that will give us 12, 2, 1, 7, 24, 25, 2, 30. We have 3, we are carrying 3 to this place. This is 4 times bar 1, that's bar 4. That's minus 4. Plus 3 that we are bringing, that makes it bar 1. Now, let us complete the transaction of the numerator. Let's complete the transaction of the numerator, which means that we are adding this one to this one for the numerator, because it's multiplication. So let us do that. 0, 5, 1, 2, bar 1. So that is the logarithm of everything in the numerator. Now, let's quickly go to the denominator. We have 0.0948, and that is bar 2. Bar 2 plus points. Let me quickly check. 94.8. 94.8. That's 9768. 9768. 9768. Because I divided by 3, I have to adjust this one for ease. And I subtract 1 from here, add 1 to this one. So that's going to give me bar 3 plus 1.9768. And what would that give me? So that will give me this one is divided by 3. Bar 1 points. This one is 6, 5, 26, 8, 28, 9. So that's what it will give me. Now to complete this transaction, everything, because this one is being used to divide this one, I have to subtract this one from this one. So the whole process, the whole answer, log of the equation is this. I will subtract this one from here. So this is 1, and this is 6, this is 5, this is 6, this is 5, this is 5 again. And then this will be bar 2 minus bar 1. That will make it bar 1. So this is the log of this expression. So now the answer is antilog of bar 1.5561. And what would that give you? 5561. That will be 3598. So 3598 times 10 to the power minus 1. So which is approximately 0.3598. So that is the answer for this thing. So you just try to make your work neat for ease in your handling the whole thing. Now I have another expression. 9.64 raised to the power 3 minus 10.5 divided by 9.64 plus 10.5 all square roots. When I look at this, for ease, we need to first of all work out what is 9.64 cube. That is the way easy. That's the way we can handle this thing with ease. So let's quickly work out this. If you have polygon table, you can check it out straight from the cube table. But because so that we can enhance our understanding on how to work these things out, I generally pick this one. So in this instance, we have 9.64. And what is the log of that? That is 0.9841. 9841. So for us to find the cube root, we have to multiply this one by 3. And that will give us 3, 2, 9, 7. So the log of that is 2.8923. So the antilog of this is going to give us, so we have 2.8923. Now, so the antilog is going to be 8923. So that is 7803. 7803 times 10 to the power 2. So that is for that one. Therefore, this one will now be equal to square root of 780.3 minus 10.5 over 780.3 plus 10.5. So what does that give us? It gives us 8 over 790.7. So that is what you are going to process now. You can see that the work is easier now. So what do we do first? What we do first is to find the log of what is inside and then we divide by 2. So let's quickly work that out. So 769.8, 790.7. So we have 2 points, 76 under 9, difference 8. That is 8864. 8864. The next one is 79 under 0, difference 7. That is 8980. 8980. So what does that give? I have to subtract. So this one is 4, 8, 8, and then 9. So this is 1. So by 1. So that is the value of this. Then I have to divide this one by 2 because I'm finding the square root of this. So this will now be by 2 plus 1.9884 divided by 2. So that will now give us by 1 point. This one is 9942. So the answer is antilog of this. Therefore, square root of 9.64 cube minus 10.5 all over 9.64 cube plus 10.5 will be equal to, let's check that 99. The antilog of that 99 under 4 difference 2. That is 9868. 9868 times 10 to the power minus 1. So which is 0.9868. So that's the way. Just please consider the process. That is the most important thing. Once you look at the process, I want you to note in this place, this is subtraction and this is addition. I have to find this one separately, did the normal addition. But if it had been division that is here, I will find the log of this one and work everything out in log. But because we have division and subtraction and addition, we don't use logarithm for subtraction and addition. You add it the normal way that you do the addition. Please take note of that.